Good morning and or afternoon, class. I hope everybody is having a fantastic day. Sorry I have been out. As you are probably aware at this point, I had a baby. I would introduce you to her, but it is 9 o'clock at night, so she is asleep. I am recording this at home on my computer. My only mic right now is my Logitech webcam. So if the volume is not loud enough, please let me know and I will try to fix that. It is coming off as fairly loud on my end as far as my measurement of the decibels being recorded is, so I'm hoping that this is okay. So I'm going to be capturing this with Streamlabs OBS, and I'll be using my fancy writing tablet thing here, so hopefully this will go smoothly. So, the other day, let me turn this thing on, I gave you a worksheet on matter and classifying matter. Now, technically the next chapter that we have is electron configuration and orbital shells, and it gets into something that is fairly confusing, actually, something that I would prefer to handle myself, or at least wait a little bit longer before we cover that. So I want to go into classification of matter today, and how we can look around and classify different pieces of matter around us. So let's start off with a recap of what matter is, of why matter matters. Just kidding, but what matter is. Oh, and as a quick aside, for a fun fact, I hope I haven't told you this one already. If I have, my apologies. So Viking populations would often mix bones of animals they had hunted in with the iron they were using to make their weapons, because they believed that the bones of the animal would imbue the weapon with the strength of the spirit of the animal. This was an idea they had that seemed to be validated, because those weapons would often be stronger. What they did not realize is they were creating a primitive steel by adding carbon to iron, creating something called an alloy. But anyway, let's get going with today's matter, and actually I think we'll probably talk about alloys a little bit later with today's lesson. So matter. Matter, if you remember, is anything that takes up space. Anything that takes up space and has mass. So, a vacuum takes up space but does not have mass. It has mass. Has mass. Right. It has to be both things, right? Take up space and have mass. We have a lot of different examples of matter, and we talked about that in class our first week. But let's talk about the breakdown of different types of matter. And I know I already had you watch a video on this. I would prefer to kind of reteach it in my own words, especially while I'm out and I can't check in with you. And I'll probably also go through that worksheet that I assigned to you. So, again, anything that takes up space and has mass. We have a few different ways of classifying matter. But our first one is an element versus a compound. an element versus a compound. So, an element is made with only one type of atom, one element from the periodic table. So a hunk of pure iron is just iron. It doesn't have to be a single atom to be an element, right? If you have an iron bar, if you have a cast iron pot at home, right, well, an untreated one, that's a pure substance. Sorry, apologies. I meant to start off with pure substance versus mixture. We just skipped ahead for a second. We have pure substance and mixture. Under pure substance, we have element versus a compound. So let's identify each of these things as we go through. A pure substance, right? That is going to be one material, only one material, all made of the same thing, basically. Same thing on a molecular level. Whereas a mixture, actually let me hide that, there we go. A mixture is two or more substances. Sustains, oh shoot. Substances. Alrighty. So move all this over. Just gonna shrink that down because we need to talk about other stuff. But again, one material all made of the same thing on a molecular level, basically. Right? It is a, again, pure substance. And we'll go over examples of all of these afterwards. Allow me move that off to the side as well. It's hard to just erase things with this app. That's the one thing that it's not so great for. Unless I can, oh, I can delete it just like that. Perfect. All right. Now when we get into elements, right? Elements are made of one, right? One element on the periodic table. And I guess we'll put in parentheses all the same type of atom. Whereas a compound is two or more elements. So I think you can see here, right, in the breakdown of matter, first we have a pure substance, which is one substance, or a mixture, two or more substances. Then we have an element, which is one element, and a compound, two or more elements. So you can kind of see how it breaks down as we go further. As far as mixtures go, we have two subcategories of mixture. We have homogeneous, and we have heterogeneous. This comes from, right, homo means same, where hetero means different. A homogeneous mixture is one that has all the same consistency. You can't tell one part from another. Can't tell parts apart. Whereas heterogeneous, right, you can tell different parts apart. So these ones, right, are these ones are rather. I apologize. I'm feeling a little unwell tonight, so my brain is a little scattered at the moment. A little overheated too. I might just take off my sweatshirt. And again, my apologies. I'm just going to keep it running because I don't want to have to splice videos together. Alright. It's important to be able to distinguish these from each other, because you need to be able to recognize that there is a such thing as a homogeneous mixture. Just because you can't tell something apart, right, doesn't mean that it's just one thing. But furthermore, homogeneous mixtures tend to be ones that we use in chemistry, where heterogeneous mixtures tend to not be ones that we use in chemistry, or at the very least, they might be a result of a chemical reaction. So let's go into each of these in a little more detail. I'm going to erase everything, but you can pause the video at any time, so just scroll back if you need to write stuff down. Right, let's start off again by talking about pure substances and some examples of this. This is anything that is not made up of more than one thing. So, one example of this would be, right, something like, well, really any element. So, something like iron, right? That is a pure substance. I don't want to just say purified. I'm going to say deionized water. That is everything but the water removed. It's actually not just purified. I'll just say pure water is only one substance. That substance being water. Right. Other examples of this might include things that need to be kept really, really pure. Computer chips are made of silicon. That is 99.999% pure silicon. Right, things like just oxygen, just hydrogen, any pure element on its own is a pure substance. And again, any pure compound as well. If we want to get into mixtures, right, mixtures are really just, again, anything that is two or more. So, tap water. There's no such thing as pure water coming out of your sink. Even if you purify it, it won't be pure water, and that's actually a good thing. You need a certain number of ions, right, of charged particles to be in your water. Otherwise, you could end up getting quite ill. And actually, drinking too much pure water would be deadly. Let me just check on our recording time here. We are at 15 minutes, about a third of the time I want to cover. Okay. Yes, drinking too much pure water could be deadly. So, we also have things like, let's see, most foods, for the most part, I can't think of any that wouldn't be, are mixtures, and not just ones where you're mixing a bunch of vegetables, different vegetables together and things like that. The food itself, right, is made up of different components. We are mixtures. We are made up of muscle and bone and skin and blood and water and all sorts of different tissues. So we are one giant mixture. Air. Air is a mixture. Right, so air is a mixture of gases. It is, I want to say, 76%. You know what? I'm having trouble remembering the exact percentages off my top of my head. Let's just use the internet while we have it. I want to say it's 76% nitrogen. Not makeup. Let me see. There we go. 78% nitrogen. Okay. 21% oxygen. Right. 0.9% argon. That is a noble gas, argon. It's quite a useful gas. And 0.1% other gases, like CO2. CO2 used to be prevalent in the atmosphere, however. That's actually what eventually led to the age of dinosaurs, because CO2 was able to, in huge amounts, cause giant flora to flourish, that is, plants. And they were able to produce huge amounts of oxygen, like way more than we have now, to an extreme amount that was able to support very large life that needed it. That large life will then, subsist off of the plants, but as those numbers changed, right, the plants get smaller, all sorts of things, right, eventually the meteors and things like that, lead to the collapse of the dinosaurs. So it was 78% nitrogen, 21% oxygen, and approximately 1%, but we can be exact, I guess, 0.9% argon. So that is mixtures. And again, we'll keep up with the breaking down the individual things, right? Elements are straightforward. Elements are anything on this table. If it's on this table and it's just that element, it's an element. That is probably the most straightforward, easiest one to get. Look at the table. Don't overcomplicate it. And then we have compounds under our pure substances, right? This is the other type of pure substance. So, compounds. Again, 2 or more elements. These are things like drugs that we use, medical drugs, well, technically other drugs too, right? Right, salt is a compound, right? Medicines are a compound. Water is an example of a compound if we're talking pure water. Essentially, a compound is just, again, any pure substance made up of 2 or more elements. So if you were to extract a chemical from something and isolate it, that would probably be a compound. For example, you can actually really easily extract DNA from strawberries. And I want to say that Mrs. Quinton does that in her class, so you can ask her about it or look up videos. DNA is all one molecule. It's all one substance, and so therefore DNA would be a compound and a pure substance. Mixtures. This is really where it gets a little more complicated for some people. Again, have our homogeneous and our heterogeneous. Homogeneity means that everything looks or is the same. We talk about homogeneity in cultures or countries. For example, the Nordic nations have high levels of homogeneity. Most people are from the same ethnicity and share similar cultural values, so their people are largely the same. Not like in an individual way, like they all think the same or they all, are the same person, but rather they're rather unified because they share all those similarities. Right? You can physically tell if something is homogeneous. Or homogeneous. So for example, most of the time, tap water. Most of the time you can't look at tap water and tell the difference from one part of it to another part. Another example is lemonade. Without pulp. In that similar vein, OJ. We know that lemonade is a mixture of things. Water, lemon juice, sugar. Lemon juice itself is a mixture of things. Water, various chemicals that make up flavors, and citric acid. So, when we look at lemonade, we might recognize that it's different chemicals, but you can't tell one part of lemonade from another. Unless, again, you're making it with a powder and there's some unmixed powder, or if it's a pure lemonade with pulp. So if you were going without pulp, things like orange juice and lemonade are homogeneous mixtures. For heterogeneous, you can probably imagine then you throw in the pulp and there is a separate substance that you could physically identify or physically feel. Right? You're drinking it and you can tell one part from another. Right? You can see the pulp floating around and you can distinguish one part from another. It is heterogeneous. Another example here could be milk. Milk is homogeneous, right? However, spoiled milk typically starts to get solid chunks in it. And these are physically different from the other parts of the milk. If we can see and feel a physical difference, then it is heterogeneous. A good example, oil and water. Oil and water do not mix. You can quite distinctly make out the two different layers. So that would be heterogeneous. Now here's an interesting one. Salt water. If you go right now and you dissolve, at least not too much, a bit of salt in water, you can't see it. It's homogeneous. However, the ocean is a heterogeneous mixture. And the ocean really is one giant mixture. We can see different parts in it. We have the salt water, but we all can also see fish, bits of waste, unfortunately sometimes trash, bits of seaweed and other sea plants, and all of the other things you might expect to find in the ocean. So the ocean is heterogeneous, even though salt water is homogeneous. Oops. Now I want to make one quick further distinction. We have atoms versus molecules. We have to ask ourselves, where does this fit in with these charts? Well, an atom is a single atom, off on its lonesome. It might connect to more atoms, but if we're going to really call it an atom, right, then this would be an element. For molecules, however, to borrow a phrase from Attorney Tom on YouTube, it depends. For those who are familiar with him, very funny content creator. If I wasn't so tired from it being late and having a baby, I would totally stick a clip of the little theme song on there with the "it depends," but you know, maybe another day. It depends. It can be an element or a compound. So the reason for this is a molecule. So an atom, right, is a single atom. A molecule is two or more atoms. Get this out of the way. Just together. Notice the distinction between this and a compound. A compound is two or more different types of atoms together. This is just two or more atoms. So all oxygen appears to us as O2. The atom, or the molecules, look like this. You'll figure out what exactly these mean later on, but maybe you've seen it before. That is an O2 molecule, or a hydrogen molecule. It just looks like this. That's H2. We also have N2, Cl2, F2, Br2, and I2. I don't recall if there's astatine, if astatine is diatomic. It might be, although we tend not to talk about astatine, seeing as it decays in about 5 minutes. So these would be elements. However, a molecule can also be different kinds of atoms. It doesn't specify that it's not that. So this is a water molecule made of hydrogen and oxygen. As we discussed previously, water, pure water, is a compound. So a molecule could be an element or a compound. So, and actually, I'll go over the diatomic elements real quick. There's only a few of them. Diatomic elements are elements that always appear in sets of two atoms. We have nitrogen, oxygen, fluorine, chlorine, bromine, iodine, maybe acetine. Again, I don't know. I'll put a little asterisk there to maybe look that up later. But again, acetine, if I click on that to show you, if I turn off drawing on the page for a second, acetine has a half-life in, oh, that's rubidium. Click acetine, 0.04 seconds. So we're talking minutes, right? Half of acetine decays in 4/10 of a second. There's not much there. Oh, sorry, that is the low abundance one. Let me go to the high abundance one. Acetine is element 85, and typically it has, let me do this right, 210. So let's look at 210. I think it should actually be about like 8 minutes, something like that. That seemed a little low to me. Let's see. 210. And let's compare these numbers. No, not 210. Well, my apologies. Seem to be having trouble finding the most common isotope. Oh, here we go. I think it's, no. Well, you know what? I will do this some other time. Yeah, I'll check back in with this. My apologies for the delay. One more. Let's just throw it on 212 and see what happens. Then move on. Nope. Okay. So, anyway, acetine decays in a few minutes, so not really that important anyway. If we were to draw a big Venn diagram, and let me check our time real quick, 33 minutes. All right, I think I'll do this, and then I'll probably end it for the day. I want to cover what we went over. Well, I'll probably try to go over the homework too. So I don't think I'll have homework this week specifically because I want to cover what I was just giving you worksheets for, and then as we get into new stuff, I'll give you homework to go with that. If we were to make a Venn diagram of pure substance versus mixture, boy, don't need a triangle. Right, these are distinct. These would be completely separate. However, under pure substance, right, we'd have our subgroups. Let me switch to a different color for this, actually. Let's go blue. Elements. Let's do green. Compounds. And then finally, if we were to throw in an orange, right, the overlap of these is molecules. Whereas here, entirely within elements, we would have atoms, a single individual atom, or a group of atoms together that are all the same, again, would just be an element. And then under the mixture, we have just the homogeneous, right, and the heterogeneous, and these are exclusive. Ignore that, should be no overlap. All of this, right, all of this falls under matter. Alrighty. So, with that in mind, I'd like to go over the worksheet that I gave you related to this. So let me pull up Google Classroom and just any one of the CPA classes, as I did assign this to all of you eventually. And we have our classification of matter worksheet. So, sorting each of these into its correct categories, right, we can say the first thing you always want to look for is just what is an element on the periodic table. We have, right, gold. Gold is an element. So is silver. Right, we have oxygen is an element. So is hydrogen. Then we look through, and actually graphite is actually a pure element. That was a bit of a hard one. Graphite is made of pure carbon. I know I mentioned that a few times in class, but you would have had to remember that one. Sulfur is also an element, right? It's right here on the periodic table. As far as compounds go, we're looking for pure chemicals. Sucrose, that's a compound. Water, now this is tough, right? I'm sorry, I should have specified. Let's just assume this is pure water for the sake I might have that in the wrong place, and if so, I apologize. It would either be a compound or a homogeneous mixture. I should have said tap water, so let's assume pure water. I can't recall off the top of my head. Right, we have carbon dioxide, CO2. That is a single chemical. Mustard gas, that's one chemical. Sodium chloride, one chemical, a compound. Calcite is a single chemical. You might not, you might look at blood for a second and not be sure as to what it is, but remember, blood has iron in it, right? But not all blood is iron. So, therefore we know it must be a mixture. But you can't tell apart, so it must be a homogeneous mixture. Now, dirty air. This makes the assumption, right, like smoggy air. This would be a heterogeneous mixture. This would be something you can look at and you could see the pollution in. Dijon mustard. If people aren't familiar with Dijon mustard, right, I would recommend looking up a picture. Good Dijon mustard has these speckles in it, where you can physically see the different components. So Dijon mustard is a heterogeneous mixture. However, yellow mustard is a homogeneous mixture. You usually can't tell one part from another. Dirty water, again, it's dirty. You can make something out in it typically, right? Usually mud or particles. That would be a heterogeneous mixture. In this case, again, water could be a homogeneous mixture if we're talking about clean tap water. But if we're just mentioning pure water on its own, go with a compound. Salt water. Salt water is salt in water. Fairly straightforward. That is a homogeneous mixture. Same with clean air. We know it is a mixture of different chemicals. It's not a compound. Air is not a molecule. Trail mix. You can see the peanuts. You can see the chocolate. Rubbing alcohol. Now this is where it gets a little tricky, right? Rubbing alcohol is often also referred to by isopropyl alcohol, but there is a difference. Isopropyl alcohol is the compound. Rubbing alcohol is the product in which we mix isopropyl alcohol with water. So if we look up a bottle of rubbing alcohol and we look at the label, it's probably going to say 70 to 90%, somewhere in that range. 70% rubbing alcohol. So 70% isopropyl alcohol, right? 70%, 70%, 70%. What all of that means, if it is 70% one chemical, it must be 30% another chemical, which in this case is water. Right? Even something that is 99% is still a mixture. So rubbing alcohol would be a homogeneous mixture. Now, coffee, at least a good coffee, should be a homogeneous mixture, where you can't tell one part from another if it's nice and smooth. Ground black pepper, right? So we can actually look, and again, I encourage you always, if you don't know something, to look it up. If you don't know the information to pick it up, so black pepper is made up of a lot of different things. It is a plant. So think about that, right? It comes from a plant. Plant material is made up of a lot of different things. It's made up of cells. Cells have tons of things in them, right? So we have all sorts of different chemicals in black pepper. We can look up a black pepper, again, plant, right? You start off as this, you dry out, you get black pepper. And again, if it is a plant, it has all sorts of cells and various materials in it. So at this point, we are probably actually looking at a heterogeneous mixture because you can tell different parts of black pepper apart. All right. And for our last one, do I have one in the wrong place? They are all supposed to be even. You know what? Sorry, I think I was thinking of the wrong compound. Calcite. Calcite rocks. Nope, that should just be calcium carbonate. I couldn't remember if they would have inclusions yet. So that would just be a single compound. All right, well, brass is going to be a compound. It's two or more elements together, but you can also actually really make the argument for, in some alloys, actually I'm trying to remember, brass should be a homogeneous mixture. Some alloys are compounds, and some are homogeneous mixtures. And it really depends on how exactly it is created. now we can look at our fill in the blanks here. Right, if we look at this is all stuff in the universe that is matter. All particles are chemically identical. That would be a pure substance. Right, all atoms are chemically identical. That would be an element, and different atoms are bonded together. That would be a compound. Different particles are combined physically as a mixture. They are not evenly spread. And I don't completely like that, but yeah, evenly spread means like you can make out the difference between them, right? You can make out the difference. That's heterogeneous. Homogeneous, you can't make out the difference. So I hope that went well for everybody. And with that, I'm actually going to call it a day. We're just at about 45 minutes. I want to make sure I leave time for attendance. So don't worry about homework today, but we'll keep an eye out, and I will let you know at the end of class when you have homework that should be on Google Classroom. So have a great day, everybody. I look forward to seeing all of you again. I really do miss being in the classroom. See you around.